In this video, we'll go over a few basic operational amplifier circuits. We'll take a look at how op-amps do mathematical operations and perform signal comparisons. We'll also discuss how to use op-amps to build oscillator circuits. The first circuit we're going to look at is the comparator. This circuit determines whether an input exceeds a certain level defined by a reference voltage. The non-inverting input is the input signal. The reference signal is defined at the inverting input. In this circuit, you'll also notice that there's no feedback circuit. Thus, this is an open-loop circuit and the gain is defined by the open-loop gain inherent in the op-amp. As we've mentioned in the previous videos, the open-loop gain is typically in the hundreds of thousands. Thus, any signal that is introduced at the input will be multiplied by this very large gain. Since the op-amp is limited by the power source that powers the op-amp, the output is always saturated. In Figure 1, the reference signal is ground or 0 volts. Every time the reference signal crosses the 0 volt reference point, the output switches from one saturation state to another. For example, in the figure, the signal begins just below the 0 volt reference. As soon as it crosses 0 volts, the output signal is positively saturated. As long as the signal is positive, the output will remain saturated and at maximum. As soon as the signal crosses the 0 volt gain, the output signal then becomes negatively saturated or at the negative maximum signal. In Figure 2, the inverting input is connected to a voltage divider, which is a positive reference voltage. In the same manner as the zero level detector, the non-zero level detector switches from the one saturation state to another every time the signal crosses the reference signal. The circuit shown is called a summing amplifier. We first note that this is similar to the inverting amplifier circuit that we learned in a previous video. The only difference is that at the inverting input, the current branches in from 2 points, Vin1 and Vin2, through resistors R1 and R2 respectively. Using Kirchhoff's voltage rule and golden rule number 1, we say that the currents I1 and I2 are just equal to the total current IT. We know that the total current is just the negative of the output voltage divided by the feedback resistance, and that the current through each of the branch is just the corresponding input voltage divided by the corresponding resistance. Equating all of these, we get the expression relating the output voltages to the input voltages. It would be easier to see how this circuit is a summing circuit if we set all resistances equal. This would cancel out all the resistances and we are left with the expression where the sum of all input voltages is just equal to the output voltage. If there are n inputs, then all of the inputs simply add up to constitute the total output voltage. If the desired gain is greater than unity, then set all input resistances equal and less than the feedback resistance. Otherwise, if all resistances are the same, then the gain is unity. If the resistances are generally not the same, then what you have are different coefficients to the input voltages, or different weights assigned to each input of the summing amplifier, forming what is called a scaling adder. Finally, you can also design this circuit to be an averaging amplifier by setting the feedback resistance divided by the input resistance equal to the reciprocal of the input of the number of inputs as seen in this example. Now let's do some calculus. The figure shows an ideal op-amp integrator. You notice that this is similar to the inverting amplifier circuit, except that the feedback resistor is replaced by a capacitor. Setting up our equation, we begin with the current conservation. We see that the current through the input resistor is just the same as the current through the capacitor. The input current is just equal to the input voltage divided by the input resistance. The charging current is defined as the amount of charge per unit time. Since the charge Q is just equal to the capacitance multiplied by the voltage that supplies it, which is V out, then IC is equal to the capacitance C times the voltage Vout divided by the charging time. Rewriting, we then have our expression for Vout and Vin. We see that if Vin is a constant DC voltage, then the output voltage becomes more negative beginning from 0 voltage. If the sign of the input becomes negative relative to ground, then the output voltage increases beginning from 0 voltage. You can see that with a constant input, the output is a constant slope, which is what integration is. The op-amp differentiator is also similar to the inverting amplifier, except that the input resistance is replaced by a capacitor. We have exactly the same equations as in the integrator, except the input becomes the output and vice versa. We end up with the expression shown. Keep in mind that the input voltage is the capacitor voltage. If the ramp input is present, then the capacitor charges linearly. As long as there is current at the input, the amplifier will drive the output to produce a constant current through the feedback resistor, keeping the inverting input equal to ground. If the input voltage ramps up, then the output voltage is negative and constant. If the input voltage ramps down, then the output voltage is positive and constant. You can now see why this is called a differentiator. Now let's consider how op-amps can be used as an oscillator and look at a few circuit examples. The circuit that we're going to study is called the Wien bridge oscillator, which produces low distortion sine waves over a wide range of frequency. To implement it, we use a lead-lag circuit, as shown in the figure. R1 and C1 together form the lag portion of the circuit, while R2 and C2 form the lead portion. At lower frequencies, the lead circuit dominates due to the high capacitive reactance of C2. Thus, the signal is highly attenuated. As the frequency increases, the lag circuit begins to balance out the lead circuit, causing an increase in the signal, peaking at the resonant frequency. Beyond the resonant frequency, the lag circuit begins to dominate. By setting the two resistors equal and the capacitive reactances equal, we can determine the output voltage to the input voltage ratio to be 1/3. The Wien bridge oscillator is obtained by using the non-inverting amplifier circuit we learned in the previous video, and then replacing the input with another feedback network connected from the output terminal to the non-inverting input. The positive feedback network is our lead-lag circuit. If you recall, the closed-loop gain of the non-inverting amplifier is just R1 plus R2 all over R2, which are the resistances of the voltage divider network. To sustain the oscillation, you design the circuit such that the closed-loop gain of the negative feedback balances the attenuation at the positive feedback. Since the attenuation of the positive feedback is 1/3, the closed-loop gain should be 3. Thus, R1 must be equal to twice R2. So how does it work? Initially, R2 is adjusted so that the closed-loop gain of the negative feedback is greater than 3. This allows the output signal to build up, fed back, and attenuated to the input. Since the lead-lag circuit is adjusted at a particular frequency, then only those input signals with phase shift equal to 0 relative to the output is amplified, as with the condition of resonance. Where did the oscillation come from in the first place? As you know, all signals, no matter how small, can be broken down into their Fourier components. The output of an op-amp is composed of all of these frequencies. The positive feedback circuit defines which frequencies are amplified, and these are the frequencies that are exactly at the resonant frequencies, or when the phase shift is 0 between the input and output signals. Once the signal has built up, then R2 is tuned down in order to balance the attenuation of the positive feedback. At this point, the signal can be sustained. The triangular wave oscillator generates a triangular wave as well as a square wave output. It has two output terminals, one corresponding to the square wave output and the other to the triangular wave output. If we set the initial output signal of the comparator to be negative, then this signal is fed into the inverting input of the integrator. The output is a signal that ramps up. Once this signal reaches the upper trigger point, or UTP, then the comparator switches to its maximum positive level. This then changes the output of the integrator to a signal that ramps down. Once this signal reaches the lower trigger point, or LTP, then the comparator switches to its maximum negative level, and the cycle repeats. The UTP and the LTP are defined by resistors R2 and R3 as shown. The expression for the oscillation frequency is also shown. This circuit is a square wave relaxation oscillator. The circuit is composed of a capacitor at the inverting input with a resistor feedback and a voltage divider network as the positive feedback circuit. The negative feedback circuit looks like a differentiator, although it technically does not differentiate the signal here. The positive feedback circuit is not just a voltage divider circuit, but also acts as a reference signal that triggers the output to change signs, just like in a comparator circuit. At the start, the capacitor is unchanged. This drives the op-amp to give an output corresponding to the maximum negative voltage. Part of the output is fed back to the capacitor through the feedback resistor charging the capacitor. Once it reaches the trigger point defined by the voltage divider, the output signal switches to the maximum positive voltage. This then discharges the capacitor, since the output terminal has less potential than the capacitor voltage. Once the capacitor has discharged or reached a minimum level, the output switches back to the maximum negative voltage and the cycle repeats. I hope you've learned how to implement basic operational amplifier circuits. These are fundamental circuits still used today even in current applications. With this knowledge, you can perhaps imagine for yourself the potential applications these can be used for. To really understand the concepts, I would highly suggest that you go through the examples in the book. If anything is confusing or you wish to clarify some calculations, don't hesitate to ask. This lesson marks the end of our Physics 173 journey. In the next video, we'll discuss a few exercises to help you gain a better understanding of operational amplifiers. You should also solve a few exercises yourself. After that, you will be directed to the link for the fourth exam.